Welcome to the Explainer. Today, we're taking a seriously high-energy journey right into the absolute foundation of mathematics. If you're gearing up for the Cambridge IGCSE Math exam, specifically syllabus-0580, then you already know that numbers are basically your ultimate toolkit. But here's the thing. To use them effectively, you've got to speak their language fluently. In this explainer, we're breaking down the core vocabulary and those specific sets of numbers that are absolutely critical for your success. We aren't just going to sit here memorizing dry definitions. We're actually going to visualize how numbers interact and literally structure our world. So let's get started. Okay, let's dive into this. We've got 4 foundational topics on the agenda today. First up, we'll explore the number universe, where we categorize every type of number you're going to encounter. Second, we'll look at the fundamental building blocks: primes, factors, and multiples. After that, we'll scale things up and down with powers and roots. And finally, we'll anchor the whole shebang in the real world with directed numbers and reality. Section 1, the number universe, building the math matryoshka doll. You know, just like shapes can be classified in a bunch of different ways, like how a square is a quadrilateral, but it's also a polygon, numbers fit into very specific categories. And honestly, the best way to visualize this is to think of Russian nesting dolls, where each new set of numbers completely swallows up the previous one. Let's walk through these steps and see how this builds. Step 1 is the smallest doll, natural numbers, represented by the letter n. These are just your basic, everyday, positive whole numbers, starting right from 0. Then, step 2 expands to integers, or z. This doll includes all those natural numbers, but it throws negative numbers into the mix. Step 3 gives us rational numbers, or q. This one gets way larger because it includes fractions, and any decimals that can be written as fractions. Finally, step 4 is real numbers, or r. This is the giant doll that holds absolutely everything, rational and irrational alike. To really cement this in your brain for the exam, let's anchor these concepts with some real-world examples. Natural numbers are super intuitive. It's like a child learning to count 1, 2, 3, or telling someone, I live at number 73. Integers step in when things drop below 0. Think of an overdrawn bank account sitting at a painful negative $200, or a freezing winter night at negative 2 degrees. Rational numbers? Well, they appear when we start splitting things up. When a kid says, I am 3.5, or 3.5. They're using a rational number. Keeping these everyday anchors in mind will make these abstract sets instantly recognizable when you're feeling the heat of the exam. So a really crucial point here is understanding the great divide in mathematics: rational versus irrational. Over on the rational side, numbers are, well, orderly. They can be written out as a nice fraction where the denominator isn't 0. And if they're a decimal, that decimal eventually stops, like 0.2. Or it repeats in a completely predictable pattern, like 0.3333 forever. But then, on the other side, we have irrational numbers. These are the rebels. They absolutely cannot be expressed as a simple fraction. Their decimals just go on and on forever without ever repeating a pattern. The most famous one? Pi. Or take the square root of 2, which stretches on infinitely as 1.41421356. You get the idea. Let's do a quick exam scenario. Is the number 0.625 rational or irrational? Think back to the rules we literally just covered about decimals. Does this number go on forever unpredictably, or does it stop? Boom! It is rational. If you guessed that, you're spot on. It's rational because 0.625 is a terminating decimal. It comes to a neat, clean end. Just remember this golden rule. All terminating and recurring decimals are rational numbers because they can always be written as fractions. All right, section 2, primes, factors, and multiples, the building blocks. Now that we've got the types of numbers down, we need to look at how they actually behave, how they break apart, and how they scale up. We've got to start with the prime number. A prime number is simply a number whose only factors are 1 and itself. We're talking numbers like 2, 3, 5, 7, and 11. But heads up, here is a classic exam trap that catches students out literally every single year. The number 1 is not a prime number. Make sure that fact is completely burned into your memory. Before we dive into factors, let's take a quick detour on a specific vocabulary word you're going to see a lot: the reciprocal. The reciprocal of a number is what you get when 1 is divided by that number. So the reciprocal of 5? It's just 1 over 5. If you're asked for the reciprocal of a fraction, let's say 2/5, you just flip it, so it becomes 5/2. It's a really simple command, but you absolutely have to know exactly what the word means when you see it. Now, what's really interesting about this is how we can take complex numbers and completely break them down into their pure prime essence. Let's look at prime factorization using division ladders for 18, 24, and 75. The most reliable method here is to just keep dividing by the smallest prime numbers in order. Take 18. Divide by 2, you get 9. Divide by 3, you get 3, and by 3 again to get 1. So 18 is simply 2 times 3 squared. For 24, we pull out 3 2s and a 3, giving us 2 cubed times 3. And for 75, we pull out a 3 and 2 5s, leaving us with 3 times 5 squared. Using this visual tree method pretty much guarantees you won't miss a single prime factor during your test. Section 3, Powers and Roots, Scaling Up and Down. Okay, we've taken numbers apart. Now let's see what happens when we multiply numbers by themselves. Let's contrast square numbers and cube numbers. When an integer is multiplied by itself, like 4 times 4, the result is a square number, 16. You're raising it to the power of 2. But when an integer is multiplied by itself, and then by itself again, like 4 times 4 times 4, the result is a cube number, 64. That's raising it to the power of 3. Understanding the difference between scaling up in 2 dimensions versus 3 dimensions is a major key here. Now let's throw it in reverse and talk about roots. And honestly, here is where things get just a little tricky. The square root of 16 is 4, right? Because 4 times 4 is 16. But look closely. The answer is actually plus or minus 4. Why? Because a negative times a negative equals a positive. Negative 4 multiplied by negative 4 also equals 16. By convention, the square root symbol usually implies the positive root. But mathematically speaking, the square root of 16 has 2 totally valid answers, positive 4 or negative 4. But wait, here is a crucial rule you cannot forget. Negative 16 has no real square root. Think about it for a second. Any integer squared, whether it starts positive or negative, will always result in a positive number. Therefore, in the realm of real numbers that we mapped out earlier, you simply cannot find a square root for a negative value. It doesn't exist. Moving into section 4, directed numbers in reality, above and below 0. For our final section, we're taking a look at how positive and negative values govern real-life scenarios. And this brilliantly illustrates the concept of distance using directed numbers. 146, that is the massive gap in degrees Celsius between the highest and lowest recorded temperatures on Earth. The highest temperature ever recorded was 58 degrees in Libya. The lowest was a freezing negative 88 degrees in Antarctica. To find the difference between them, you take 58 and subtract negative 88. And since subtracting a negative is the exact same thing as adding, we get a massive 146-degree difference. You're going to use directed numbers all the time in everyday applications. Calculating the height of an apartment block roof that's 130 meters above ground level compared to its parking garage that's 35 meters below ground level, that requires directed numbers. Managing your bank statement, trying to balance positive credits against negative payments, directed numbers. Even calculating how far a submarine, currently 165 meters below the surface, needs to dive to reach the ocean floor 860 meters down. Mathematics isn't just marks on an exam paper, folks. It's literally the invisible language describing our physical reality. Wow, we've covered a massive amount of ground today, from the core sets of natural and rational numbers, diving down into the building blocks of primes, and scaling way up with powers and roots. So I want to leave you with this final thought. From counting on our fingers to calculating the absolute extremes of our universe, which set of numbers do you rely on the most? The next time you check the weather, look at your bank balance, or even just cut a piece of cake, take a second to remember the mathematical universe operating quietly in the background. Thanks for joining me on The Explainer today, and keep exploring.